Trigonometry, three-angle measure, or the measurement of three angles. Now, if you are taking trigonometry, you just had a big aha moment there, but if you're not, well, now you know. Anyway, in this video, we are going to be learning about trigonometry. So let's get started. Okay, before we start in this lesson, let me talk about similar triangles. Now, what are similar triangles, or just what makes anything similar? Well, a similar object has the same shapes. I'll just write that here. Similar means same shape. Now, this does not necessarily mean the same size. Let me give you an example here. Let's say we have this shape here, and this shape is similar to this shape if I scale this up. These two have the same size, but they're not necessarily, these two have the same shape, but they don't necessarily have the same size, and that's what makes it similar. Technically, similar objects can have the same size, but it doesn't need to. It just needs to have the same shape. So, now that we know what similar means, how can we tell if two triangles are similar? Well, what makes up the shape of the triangle? The angles, right? The angles of the triangle determine the shape. So if we know that all the angles of a triangle are the same or congruent, then we know that the triangles are similar. So let me write that down. Angle, 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 which means that if we know the three angles are the same, means similar. Now, actually, in math, you won't see it written like angle, 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 or three angles need to be the same. You'll actually often see it as just angle, angle. But how do we know if they're the same with just two angles? Don't we need three angles or all of the angles in the triangle to know if they're the same or similar? Well, that's actually not entirely true. Let me give you an example here. Let's say in this triangle, we know that this angle here is 30 degrees. And this angle, because I wrote it like this, it's a right angle. So we know that the angles of a triangle sum to 180 degrees. So I'll just write this x here. So the right angle, or 90, plus this angle, which is 30, plus x, which is this angle here, equals 180. Right? The angles of a triangle sum to 180. Now, with the fact that we know that the angles of a triangle sum to 180, we can solve for x here because we have an equation. And it's actually true for any triangle. If we just know two of the angles, then we automatically know the third because the angles of a triangle sum to 180. So, it's actually written angle, angle because we only need two angles. Now, one more thing before we get into the main lesson. Let's talk about right triangles specifically. Right triangles. Now, for a right triangle, we automatically know one of the angles, right? It's 90 degrees. So we actually only need one extra angle. So it's not commonly written as just angle, but I'm just going to write it as angle. If we just know one of the angles, and we know that it's a right triangle, then we know it's similar. Okay, now let's finally get on to the main lesson. Say we have a right triangle with side lengths 45, not side lengths, angle measures 45 degrees, and side measure, say this is 7, and this is also 7. So, now, what is the hypotenuse, or the side opposite of the right angle? Now, the hypotenuse is 7 squared plus 7 squared, square root, according to the Pythagorean theorem, right? Let me just explain that. So, according to the Pythagorean theorem, and if you don't know the Pythagorean theorem, you can look it up on YouTube. c squared equals 7 squared plus 7 squared. Or that c equals the square root of 49, which is 7 squared, plus 49. Or that c equals, let's see, this is square root 98, right? And we can write that here. So c is square root 98. 98. Okay. Now that we know that the c is square root 98, we can do some trigonometry with this triangle. Let's say we just define a function, sine. And sine of an angle is the opposite side over the hypotenuse. Okay, I just introduced a whole lot there, so let me break this down one by one. So we're just defining sine of an angle. We're just defining it. This is not something that you should already know. We're defining it right here. And basically, what the sine function does is it says if we have a right triangle and we know one of the angles, and we plug that into our sine function, that will be equal to the opposite side over the hypotenuse. Okay, a lot of questions may still be in your mind. Why does this matter? How does this work? Any of it. So, let's go over it. Let's say we have this triangle here, and we know one of its side lengths are 30 degrees, and we know it's a right triangle. And let's say its side lengths are 6 and 12. Well, what the sine function says is that the sine of 30 degrees is equal to the side opposite of the angle divided by the side, the hypotenuse, or the longest side. That's equal to 1/2. Well, a lot of questions might be popping up in your head, like, how is this useful? Why does it work? Well, let's first go over why does this work. Like, what if this triangle had the same angle measure, but different side lengths? How would that work? Well, if the side lengths had one other triangle had the same side length, then they would be similar, right? If we know one other angle besides the right angle, then they're similar. Well, then if they're similar, then they have the ratio of the side lengths are the same. And just to help you understand what it means for the ratio of the side lengths to be same when they're similar, let's say we have this triangle here, and I'm going to copy this triangle over and scale it up. All right. Now, if this side length is 7 and this side length is 14, then if we scale it up, the ratio of the side lengths, let's say we scale it up by a factor of 2, then each of the side lengths is going to be multiplied by 2. So this 7 here is going to become a 14, and this 14 is going to become a 28. Now, if you notice, the ratio of the side lengths, the ratio of, let's say this is side length A and this is side length B, the ratio of A to B in both of the triangles are 1/2. And this kind of makes intuitive sense, right? If you scale it up, then the side lengths might not be the same, but the ratio of the side lengths are the same. If you want a more concrete proof, I can do that for you right now. Let's say we have this side length with side lengths x and side lengths y, and we scale this triangle by 2 so that the side lengths become 2x and 2y. Well, the side lengths y divided by x, for the first triangle, that's just y divided by x. And for the second triangle, it's 2y divided by 2x. Now we can simplify this fraction, so it just becomes y divided by x. So the ratio of the side lengths for both of them are the same. And this is true only if they're similar, and because we scaled it up, so they are similar. Okay, so now hopefully you understand why the ratio of the side lengths are the same. But let's tie this into our sine idea. Well, if we know that one of the angles is 30 degrees, then we know they're similar. So we know that the ratio of these two side lengths are going to be the same. So now we know why this works for this specific triangle. It will work for any triangle with side length 30 degrees. But why does this work? Well, not why does it work. Why is this useful? Well, let me give you an example to how this is useful. Let's say we have this triangle here, again with side length, not side length, angle measure, 30 degrees. Oh, yeah, of course the video, I probably said side lengths a lot, but just know that I meant angle measures, if applicable. So if this angle measure is 30 degrees, then we know that the sine of 30 degrees, and remember in our previous example, we discovered that that's 1/2. And let's say we know that this side length here is 7. Now, how do we find this hypotenuse side length? Let's say we want to find it. Now, normally, you need the Pythagorean theorem for this, but actually, with sine, we don't need the Pythagorean theorem. If we have sine of 30 equals 1/2, so 7 over this angle C, which is just sine 30, equals 1/2. So 7 divided by C equals 1/2. And you can do a bit of math here to find out that C equals 14. Let's reflect on what we did here. We used the example of sine 30 for one triangle, and then we can use that example to find side lengths for any triangle. And let's say we didn't know sine 30, we could just plug it into a calculator and then find it out. If this was sine 40, we could plug it into a calculator and do sort of the same thing. All right. Now, I didn't leave this in the video because I wanted to leave it as a challenge for you. There's still other sides of the triangle, right? What about this side? How can we relate this side B to the hypotenuse C? And I encourage you to try to do the same thing in this video with side lengths B divided by C. And if you want to know, then you can do it. But if you don't want to do the homework, then you can just look up cosine, and that should give you the information you want. All right, I will see you in the next video.